Neural networks are frequently misrepresented in popular media as literal digital brains or impenetrable black boxes. To understand how they actually learn, we have to discard the biological metaphor and look at the strict mathematical structures underneath. This diagram shows the standard biological analogy. In this model, a neuron receives inputs, labeled here as x1 through xn, aggregates those signals, and if the total signal is strong enough, it fires an output, y. This diagram shows the mathematical translation of that neuron. It is a rigid graph node where inputs are first multiplied by specific weights. Those weighted inputs are aggregated via a sum, and then passed through a nonlinear activation function to produce an output. Feeding data through this structure from left to right constitutes the forward pass. The network computes the inputs layer by layer, eventually resulting in a baseline numerical prediction. A neural network is simply a cascaded series of logistic regressions. Logistic regression is a statistical model that uses a logistic function to model a binary dependent variable. The network's capacity for complex modeling is a direct consequence of how we stack these fundamental mathematical units. This brings us to a core architectural question. If a single, incredibly wide layer of nodes can theoretically approximate any function, why do modern engineers insist on building deep, multi-layer networks? This diagram shows a shallow network modeling a sawtooth function. It provides a clean mathematical proof of the limits of width. To model a sawtooth with n teeth in a shallow, single-layer network, you are forced to use 2 n nodes. The scaling is strictly linear. Watch what happens when we apply a deep, multi-layer architecture to that exact same function. We feed the output of a single tooth through the network iteratively. With every cascaded layer we add, the number of linear pieces, or teeth, in the output doubles. In a deep network, the parameter count only scales linearly with the number of layers you add. However, the functional complexity, the amount of linear pieces the network can model, scales exponentially. Because the complexity of the model grows exponentially faster than the number of required parameters, depth mathematically beats width. This geometric advantage forms the foundational architecture of deep learning. Upon initialization, the weights inside the nodes are arbitrary. Consequently, the prediction generated at the end of the first forward pass is entirely random. We need a rigorous method to evaluate its accuracy against a true known label. We measure this inaccuracy using a loss function. Specifically, we use sum of squared errors. This metric squares the numerical distance between the network's prediction and the actual target label, giving us a quantitative measure of failure. This diagram shows the loss landscape. It is a multi-dimensional space where the vertical axis represents our total error. A high error initial state leaves our network resting high on a slope. The objective is to find the global minimum. To descend, we rely on gradient descent to adjust weights iteratively. The mathematical sign dictates direction, and its magnitude determines the step size. Navigating this multi-dimensional terrain requires exact data. We have to figure out precisely how much each individual weight across the network contributed to the final error. That requires information to flow backward. We distribute the blame for the final error backward through the network's layers using an algorithm called backpropagation. Backpropagation calculates the gradient of the loss function for every single weight by working sequentially from the output back to the input. This diagram shows a simplified neural network graph detailing the calculation of delta at the output node. Delta represents the derivative of the loss function with respect to the weights. We compute this using the chain rule, a calculus formula to find the derivative of a composite function. Once delta is calculated, we update the weight. The exact change applied is proportional to 3 variables: the learning rate, the calculated delta, and the preceding node's activation. Updating hidden nodes is a challenge because they lack true external labels. To calculate their delta, we pull the delta from the succeeding layer and multiply it by the specific connecting weight. Backpropagation is a system of proportional blame. Large node activations that contribute heavily to an incorrect prediction receive the largest mathematical corrections. Here we encounter a critical mathematical friction. The exponential depth that gives the network its analytical power also threatens to destroy the backward pass entirely. This chart shows the traditional sigmoid activation function and its corresponding derivative curve. Notice the strict mathematical limits of this geometry. The derivative's maximum possible value is exactly 0.25. Because backpropagation relies on the chain rule, we repeatedly multiply these local derivatives across layers. Multiplying fractions less than 1 is unforgiving. Raising 0.25 to a 10-layer depth causes the error signal to decay exponentially, shrinking the delta to a microscopic fraction. Bounded activations cause early layers to receive weight updates of effectively 0. Learning fatally halts. This failure state is known as the vanishing gradient problem. To bypass gradient decay, engineers introduced a specific mathematical intervention, the rectified linear unit, or ReLU. This chart shows the ReLU function and its derivative step function. ReLU outputs the input directly if it is positive, and 0 otherwise. For any positive input, its derivative is a constant 1. Multiplying by 1 allows the gradient to pass backwards through infinite layers without fractional reduction. This intervention comes with a severe structural trade-off. For any negative input, the derivative is exactly 0. If a node receives a negative input, it ceases to pass gradients entirely. This creates the dying ReLU phenomenon, a state where a dead neuron casts a permanent mathematical shadow of 0 gradients on all upstream connections. While ReLU successfully preserves gradients for active pathways, the risk of permanent dead zones proves that choosing the right activation function is necessary, but not sufficient for network survival. Even with the correct architecture, network survival is dictated by its genesis state, parameter initialization. If you start a network with identical or uniform weights, the gradients are perfectly symmetrical. The network locks into an untrainable state because the weights will never diverge. We require stochastic, probabilistic initialization to break that symmetry. However, blindly picking random numbers leads directly to the signal either compounding to infinity or instantly saturating the activation functions. This diagram illustrates the core mathematical law of initialization, defined in the literature as equation 2.5. To keep the network stable, the variance of the output signal must be strictly controlled to equal the variance of the input signal across every single layer. Variance is a statistical measurement of how far each number in the set is from the mean. If this equation is unbalanced, the numerical signal either explodes or decays to 0 during the very first forward pass, well before backpropagation can even begin its work. Without strictly preserving variance during the initial forward flow, the mathematical structure is flawed before it ever attempts to learn. To satisfy the variance balancing act, researchers developed a specific mathematical protocol called Xavier initialization. Xavier initialization forces the expected value of the starting weights to be exactly 0. It then precisely tunes the variance based inversely on the number of input nodes feeding into the layer. Drawing initial weights from this specific calculated probability distribution provides the exact mathematical starting point required for gradient descent to function safely without shattering the network. A functional deep network relies on 3 rigid pillars: the exponential mapping capacity of depth, the undecayed backward pass of ReLU, and variance control of Xavier initialization. Deep learning is a system of strict mathematical constraints. By mastering the forward flow of variance and the backward flow of derivatives, we engineer the architecture required for universal function approximation.